Okay, folks, we are on to the next mini lecture, which is about cyclic patterns in consumer resource interactions. There's two T's in patterns. Cyclic patterns in consumer resource interactions. And so this is going to be a little mathy. A lot of the ways in which we understand how populations of predators and preys interact with each other are done with systems of equations, right? Where we use a bunch of math and then we figure out the state of a given system and how it changes over time. This is often done with math. I'm not great at that math, and so what I'm going to try to do is take a really classic example of these cyclic patterns called the Lotka-Volterra predator-prey model. Lotka-Volterra predator-prey model. And walk you through it to give you some intuition about why it makes sense. And then we'll talk about how these cycles happen and why they happen. If you really like this kind of stuff, dive into it in the book. But I really want you to understand broadly here that we use systems of equations to understand how these populations change, that these are based on intuition and thought. They aren't just made up mathematical equations, and that then we can use them to predict real patterns in nature. So that's the big idea of this mini lecture, but it's going to involve us drawing some equations. Okay, so the Lotka-Volterra predator-prey model is this model where we're trying to predict a two-species system, where we have predators, and we're going to represent those as P, and we have prey, and we're going to represent those as N, right? P is the number of predators in our system, N is the number of prey in our system, right? And if we want to try to write down equations about how the changes in these populations happen over time, we would write that as d n dt. The change in population size of the prey over time. dn over the change in time. And if we wanted to talk about how prey populations change, we actually already covered that in our previous weeks, right? So the first thing we know is that populations grow logistically, right? This is via birth, via that term r, the growth rate, right? So we can have some term called r, and that's the growth rate, and you multiply that times the population at a given time, and that'll tell us how many individuals are born, right? That's the growth rate. We should label these things so we remember them. So this is predator pop. This is prey pop. R is growth rate of prey, right? Okay, so at every step, we're going to first multiply the population of the prey times the growth rate. And then at some point, prey are going to die, right? And in the simplest version of these Lotka-Volterra models, the way that they die is they get eaten, right? And so you imagine a situation where these predator-prey models, we've talked about this, where predators, what limits predators eating is their encounter rate, right? And if there are lots of predators and lots of prey, if the population of P is large and the population of N is large, then the encounter rate is going to be very high, right? This is multiplicative in this case. So we're going to say that they're going to have this encounter rate, which is N times P, and then we're going to add one more constant here, A, right? Which is the likelihood of, the likelihood of this interaction killing some of the prey, right? And so in this case, if P is 0, if there are no predators in our model, then the death rate of N is 0, right? There's no intrinsic death rate, right? Because, N times 0 times A is 0, so then the population change is just the growth rate, right? The same is true here that if there are no prey left, that's 0, then the change in the prey population is 0, right? Does that make sense to you? Okay, so this is a simple model where we just have logistic growth and encounter dependent mortality of the prey, right? And we should add here, this is R, and A is a constant that describes how often prey get killed when they encounter predators. How often skull and crossbones, N with P, right? Okay, so there's the equation that describes how the prey population changes in a simple Lotka-Volterra model. Let's do the same thing for the predator. So dp dt, the change in the size of the predator population with time. First thing is there's no intrinsic birth rate. Here, we're talking about that each time a predator eats a prey, it's going to help that predator grow, right? And so there's an encounter rate here, just like that same encounter rate up here, which is n times p, right? So if n is 0, then there's no encounters, then the growth rate is going to be 0, right? And here we have two constants. We have a, which is that same constant from before, how likely the predator is to kill the prey if it encounters it. And then b, which is a constant for how many prey the predator has to eat to gain 1, right? So if b is 0.5, that means that you need 2 prey to make 1 predator, right? If b is 6, then you need, 1 over 6 prey to make a predator, for example. Does that make sense to everybody? So again, we have n times p. This is that encounter term from up here. We have a, which is the constant that tells us how likely that encounter is to result in a predation event. And then we have b, which is a constant that tells us how many prey are needed to make 1 predator. Prey to predator constant. Okay, so that's the birth rate. That's the growth rate here. And then we also have m times p. So the way that predators die here is that there is some intrinsic mortality rate. They die, right? And so what we can see here is that if n is 0 in this equation, then the growth rate of the predator population is 0, or negative because some of them just die in this simple Lotka-Volterra model, right? Does that make sense to everybody? So let's write this really clearly without all these notes here. This is intrinsic death rate. And we should label that as m, death rate. This is the simplest version of this model. So we have dn over dt equals the growth rate of n minus a constant that tells us how often these encounters are deadly to the prey, and then some multiplicative combination of the number of prey times the number of predators. The change in predator populations over time is equal to the encounter rate of prey and predators, that same constant, plus a constant that tells us how prey are converted into predators via energy, and then we have some intrinsic death rate of the predator. This is Lotka-Volterra in its simplest sense. You could imagine that we could add things like m2n, right, which is like the intrinsic death rate of n, but that can also just be calculated into part of R. So don't worry too much about extensions of Lotka-Volterra. This is the one I want you to be aware of, right? So hopefully talking it through made sense to you there. So what's cool about this system of equations, and we're not going to do all the math to show it, but is that it leads to cyclical patterns in population dynamics, right? It leads to cyclical patterns in population dynamics. This is figure 1214 in your book. I'm going to draw it by hand, but you should be intimately familiar with figure 1214. I'm going to do my best to explain it simply, but I want you to think through understanding 1214A, 1214B, 1214C. And this is the kind of thing that explains why there are cycles here, right? Why there are cycles here. But we're just going to draw 1214D, which is on the x-axis time, and on the y-axis number of individuals, right? And this is either P or N. N or P. Okay. Okay. So what I'm going to do is I'm first going to draw the prey line. And they're going to start out at a low abundance, right? And then I'm going to draw the predator line. They're going to start out at a relatively high abundance. Oops. We're going to draw prey in blue. Or sorry, predators in blue. They're going to start at a relatively high abundance. What's going on, my friend? Oh, we're white. In this case, when n is very small and p is very large, right? N is very small and p is very large. The probability of n going up is pretty high, right? Because we have this is largely driven by growth rate. because the encounter rate is quite small because there's not very many n's, right? So what happens in this situation is that there are not enough prey to eat, predators start to die, and prey populations rise, right? That encounter probability is very low, right? That encounter probability is very low because n is small. It's hard for predators to find prey. So the prey population is driven by its growth rate, and the predator population starts to plummet because of this intrinsic death rate. When those numbers cross, we have a different situation where the encounter rate is incredibly high, right? And that means that the growth rate of the predator starts to go up, right? That growth rate starts to go up. The encounter rate grows up because n times p is big, a is big, b is big. We start going up, right? At the same time, the death rate here, n times p, is really large, so the negative number is large, so the change begins to be negative, right? Does this make sense to y'all? And this causes these cycles, right? I'm not going to draw everyone. But what you have to see here, right, is that when the encounter rate, which is driven by the number of predators and the numbers of prey, when the encounter rate is really high, then death of the prey is high and growth of the predator is high. When encounter rate is very low, then the population of the prey is driven by its growth rate. The negative portion of this equation is low, and so it's a positive slope. And instead here, this is very small, and we have death driving it. Does that make sense to everyone? Take a look at the phase diagrams. I really want you guys to understand the phase diagrams, figure A, B, and C. If you have questions about those, come talk to me about them in office hours, but for right now, I just want to focus on this in this lecture. So this is a simple way in which predator-prey dynamics, described simply, right? Simply a product of us telling logistic growth, encounter probabilities, and intrinsic death of the predators can lead to a cyclic nature. What's really cool about this is that this is a simple model, but we can see these Lotka-Volterra dynamics can be replicated in nature and in the lab. So this is a case where some simple equations are predictive. They're real in the lab and in nature. We can see these happening. Now, they're not always real. There isn't always cyclical patterns of predators and prey because there's a certain set of values for A and B and M and all these other things that go into these more complex models that cause cycles and some that just cause population collapses. But what's really neat here, right, is that this is a simple model that nature actually follows. This is some actual predictive ecology, so that's cool. Okay, that's as much math as I think we're going to do in this week. Bye.